things. At least that's my goal for today. So let's go ahead and start off with glucose bound to a fructose. Remember, that's a type of bond called a glycosidic bond that exists between glucose and fructose. What do I have if I have those two bound together? Not maltose. That's two glucoses.
Does it start with an S?
Yes.
Is it sucrose?
Sucrose. So I have sucrose. And if I take my sucrose and I put it in water, the sucrose can break down into its components, glucose and fructose. It can break down into its two monosaccharides. So I'm suggesting that bond that you're seeing right here, this bond right there, could be broken if you put it in water. Now here's the kicker. The kicker is that when we put this in water, it's not an overnight process, nor is it an over-year process. If you put just a couple of grams of sugar in water, it takes on the scale of like 20 years for this sucrose to break down. 20 years is a long or a little time? Long time. Now, could we agree, does your body do this process? Do you break down sugar? Definitely. That means you have to break this bond. Have you broken down sugar in your body?
Yes, sir.
If you hadn't, you'd be like a big bag of sugar walking around. So you've done this reaction, but you're all under the age of 20 years. So what makes something like this possible? An enzyme, a facilitator. It's a lot like saying that I have a locked door and I can unlock the door. The reality is that without the key, how does the door ever become unlocked? Eventually the door just falls down. But how long does that take? Maybe 100 years, depending on the structure, the integrity of the building.
And even then, it might need agitation just to fall down to begin with.
Now, the idea would be is that eventually it's going to decay down. It's going to break down. Give it even a billion years, that door is going to fall. It won't last forever. But we don't have a billion years, because typically if you have a locked door in front of you, you're trying to get through it because there's a need for you to. So the facilitator there would be a key for sure, right? And so your key is like an enzyme. And what an enzyme is an enzyme is basically a biological catalyst. Now then, a lot of people are like, well, what's a catalyst? Well, let's go there then. A catalyst is basically a component, it's a chemical, that facilitates a reaction without being consumed by the reaction. In other words, it's reusable. It's also very specific. And lastly, one thing that it does is it lowers the activation energy. Think about a door, you're going to have to push or pull a door to open it. But the push or pull is quite difficult if the lock is engaged. If you disengage the lock with your enzyme, with your key, that catalyst, well then the door would just simply be able to move. It would take much lower energy to move the door. Can you reuse a key? Absolutely. Could you imagine the world if you had to, like, when you bought your car, you had to be given, like, or you had to go purchase, like, 1,500, 2,000 keys to be used and just, like, basically be used up each time you started or unlocked the car? What kind of a world would that be? That would be a world of, like, keys. forget like carrying stuff in your purse would be a big key ring. So we avoid that tragedy we avoid that tragedy in real life and in biology too. Me?
Yes.
Okay.
So the two examples that you gave us, would they? I guess they would be considered likely events since it's breaking down, but
Not necessarily, and I'll show you real quick.
okay.
Using your notes from yesterday and the powers of Campbell and Reese, could you go ahead and fill this in for me? You can draw those two out if you'll fill them in for me. So, what did we get? I think we should have put reactants over on the left, products on the right, reactants left, products right. Tell me about my delta G in the case on bottom. Delta G is positive or negative? Positive, which makes this graph endergonic. There was some confusion, I think, that existed yesterday between that and endothermic. Endothermic is a reaction that would cool down the container, a reaction that absorbs heat. This is a reaction that just absorbs free energy. There is a difference. Heat isn't necessarily free energy. In this case, it looks like our delta T is going to be what? Positive or negative? Now, let's go back to that real quick. Which do you think is a likely reaction, the top one or the bottom one? The top one, because it's exergonic, right? Because there's a release of free energy. Remember, whenever there's a release of free energy, it's going to be a reaction that could happen. If there's a gain of free energy, it's going to be unlikely. Because a gain of free energy means something has to power it. Good? Now, your question was like, give me into this likely, unlikely process now with the word enzyme. An enzyme really is not likely, nor is it unlikely. An enzyme is just something that can facilitate that initial need that a reaction has. Here's what an enzyme does in either which case. This is the reaction in purple with no enzyme. Here's the reaction in brown, see, color brown, with enzyme. Here we go. I'll do it with some dots too to kind of avoid any confusion. What have I done since using the enzyme? Which is kind of where we were going with this statement. You lower your activation energy. So that's a nice way of saying that you make the process more likely because you lower the requirements for any process, whether it was a likely or an unlikely process. Whether it was a process that didn't require free energy and release free energy, or it was a process that did need it. So an enzyme is a facilitator of the reaction, regardless of if it's going to happen or not going to happen without an input or decrease in free energy.
Okay, but does the enzyme need energy at all, or does it just happen?
The only energy that goes into an enzyme is the process of actually making it.
Okay.
It's like saying, do I have to feed my key electricity? No, but there was electricity in coal or whatever else used when they were cutting it.
Okay. Thank you.
Mm-hmm.
I like your ease.
Thank you. So again, enzymes don't really use energy. The only thing that they do is they facilitate a process. They lower the energy requirement.
Like, the way that they lower the energy requirement, is that just by letting the two substrates go together?
Or the one
like,
substrate or whatever.
collect it
Yes.
and break it up? It's
Yes.
Like, the only thing they do is just like collect it?
More or less. Yep. Cool? Cool. Can I move this? So, let's spend some time talking about how these enzymes react with their substrates. Let's go over some key terms. What's a substrate?
What goes into the enzyme?
Okay, so it's basically the reactant that binds to an enzyme. When your book mentions the lock and key model, what are they referring to?
Yeah, one specific substrate can only go to one specific
Okay. So the relation maybe between substrate and enzyme is very specific. Okay. What's the active site?
That's where the substrate bonds.
It's a site or location on the enzyme where the substrate binds. Okay, so I have a picture I want us to draw real quick. So I think it could help us out. Now I don't really care how you do it specifically, but somehow we need to draw something like this. Let me outline this guy real quick because I think it might help us see what's up. let's talk about this picture though. And what we're seeing here is we're seeing initially the substrates. And what's the substrate? What is that a fancy word for?
Reactive.
Okay, so the reactants. And we're seeing them come in, and they're binding to this big guy, which is the enzyme. And they're binding at a specific location. What's the name of that location that we're seeing, like right there? The active site. Now, I would say this combination that I'm seeing here of both enzyme and substrate together would be called the enzyme-substrate complex. The reason the term enzyme substrate occurs together is because there's an enzyme and a substrate together, complex, because there's multiple objects. Now, it's right through here, during this phase, where you have the facilitation event. You have your enzyme that is somehow allowing a lowering of activation energy by speeding up the chemical process. So right through here, I'm just going to put like a little asterisk, and I want us to realize that the enzyme facilitates the chemical change. It's able to do that because it orients the chemical components, the substrates, in a way that enhances their ability to form new bonds or break old bonds. Now, in the end, you'll notice that your substrates no longer have that distinct shape, and they even try to show you with a little bit of color here. What does that mean has happened to your substrates? Yeah, they changed. Now they are products.
Is there a more scientific word for that, or no? It's just products.
Just products. Sorry to be so boring. They beef up the reactants with substrate, then they leave the products the same.
It's antimatter. Anything that substrates turns to.
Now here you still have your enzyme. And describe the enzyme's look compared to the original look. It's essentially the same, right? Which means that it could be reused. It's recycled. Now, another point to make is that a lot of times these enzymes that we're seeing are proteins. So this guy right there is a protein, and he's a protein the entire way through because it's still a protein. What do we know about proteins? They have unique shapes, right? Off to the side, we might want to jot down just some facts about proteins we know. And the first fact is that we know that they have a very elaborate but a very specific shape. Now, this elaborate but specific shape is unique only to that one protein. Where did the directions for that shape come from? Sorry, what?
DNA. Is it like possible for people to have like enzyme deficiencies?
All the time.
Like what's an example of a disease that would be that?
Does anyone have a Diet Coke in the room?
Diet Coke?
On the back of a Diet Coke, you'll see that people that have an issue with phenylalanine need to not drink it. And that's because they have a condition known as PKU, which is known as phenylketonuria, and it's an ability to break down phenylalanine. So if they ingest phenylalanine, they don't break it down. You're like, why don't they break it down? That's the same thing as saying like, why can't I get into your house because I don't have your key? They can't break down phenylalanine because they don't have the enzyme.
Is it kind of like celiac too?
What?
Celiac, where you can't
There,
break glucose?
exactly. There's a slew of genetic conditions that exist. And it's basically the people, they say, well, I have an enzyme deficiency, which is true. They do have an enzyme deficiency. But we could point that back to a larger reason. That's because you inherited, or your DNA somehow became mutated so that you no longer produce that enzyme. It's like saying that, why can't I make scrambled eggs anymore? Because I don't have the recipe for it. I tore it out. I got angry one day. So I don't make scrambled eggs anymore. Oops. Yes?
Is that kind of how, like, having allergies, like, to certain foods work?
It could be a little bit the same, but allergies are going to be an increase of a chemical called histamine in your, wherever, like, you have the, like, allergies. I suspect, like, your face, maybe. And that's actually due to a chemical called histamine increasing in its amount. But the reason allergies do affect is because allergies are binding to certain proteins in your immune system. So it's the same concept of protein-specific shape, but it's not an enzymatic protein that you're looking at in your case. But the concept is the same. We're talking about different shaped combos, different shaped objects doing or eliciting a cellular response. Now, and as you can see here, I've got products at the end. I could take another substrate or another set of substrates and put them in, right? I could put in substrates all day long. Now, you could imagine, though, there's a point in time where there's no more substrates. You're like, why? Well, because they've been converted. Tell me what goes into making this protein. What are the monomers of that protein? The amino acids, right? The amino acids are the monomers of the protein, correct? And I need those monomers back out so I could remake a different protein later on, so that I can make a different protein for a different function. So I've got to break down the protein. Or sometimes, maybe not just break down the protein, I need to turn off the protein. So now that we understand how these enzymes work through our picture, I think we want to get into like a little bit of how this regulation could affect. So let's talk about what can I do to my enzymes.
What do you think the inhibitors, whatever they're called?
A little bit. Breaking enzymes. It can be good or bad. It depends. Let's talk about the real rough ways, the quick ways. Your two most notable quick ways are going to be to change the pH or to change the temperature. If you put an enzyme in an oven, increase its temperature, probably going to break. You put an enzyme in a bad pH, probably going to break.
So is that like an example like when a lysosome is just kind of dominant?
Or, yeah, fuses with a lysosome, basically. Now, I've got a picture to show you real quick. Question? Let's look at this picture real quick. It's a graph. And you notice the top graph. Do you see the black line? Kind of that negative x squared parabola upside down thing going on? Okay, you can see where it says optimal temperature for a typical human enzyme. And it seems like, what's the optimal temperature of the black line?
38.
Yeah, 38, a little bit under 40, right? Which happens to be about your temperature. Now look at the red line, though, which is an optimal temperature for an enzyme of a thermophilic, which is a bacteria that loves heat. Tell me about its enzyme optimal temperature. 78, a little bit below 80. Now you put your enzymes in 80. Do you know what happens? They dissolve down to nothing. That's like saying I put my key in a temperature that was like 2,000 degrees Fahrenheit, and I expect it to work in my door. The key's gonna melt. You're melting the enzyme. But notice that different enzymes have different melting points, as they say. And the reason that would be is because sometimes they're found in different objects. Look at the bottom level. The black line, it says the optimal pH for pepsin, which is a protein that you would find in your stomach, an enzyme of the stomach. Notice, what is its optimal pH? About 2? What's the pH in the stomach? About 2. If the optimal pH for pepsin was like 7 and it worked in the stomach, it would never work because the pH in the stomach is always 2 or close to it. How about the red line? Optimal pH for trypsin, which is found in your intestines. A little bit basic. If I took trypsin and I put him in the stomach, what would happen? Yeah, he wouldn't work. Now, we've just said the obvious. It didn't work in a different place. Got it. But think about the implications and think about the control that this brings to the table. Now, certain enzymes in your digestive tract can only work in certain areas based on pH. Remember, your stomach is not a human, nor is your small intestine. It doesn't have eyes, nor eye sockets, nor a brain. It can't see who's there and who's not there. The only way to regulate things that are chemical like that are by chemistry. So this would be a good way to regulate an event like that. That's a good picture, I've always thought. Now let's talk a little bit about cofactors. When we think about co, what's that prefix co go for? Yeah, something that helps. These are non-protein helpers. coenzymes are organic cofactors. A good example of a coenzyme would be like a vitamin. B6, B12, all the vitamins that you ingest. How about inhibitors? Oh, go ahead.
It's just like a question with vitamins. So it's like, you know, if you're vitamin D deficient, you can't really like absorb the calcium. So it's like, does that just kind of like latch on to like the enzyme? And it's not in the active site, correct?
Correct. It depends if it's competitive or non-competitive. But if we look real quickly and we break that down into two components, we could talk about the inhibitors that are competitive. We could also talk about the inhibitors that are non-competitive. They're competitive, they bind to the active site. Bind to other site. I'll just show you this picture real quick. It's in your book, but I just kind of want to give you the animation a little bit. Do you see right here? This is what I would call a normal case. You have the enzyme, the substrate, and the active site. And do you see anything blocking it? If I was to take my little pair of scissors and cut this out, it would fit perfectly right in there, wouldn't it? Now look here. Blockage, right? There's your substrate, your enzyme. Can the substrate bind to the active site?
No.
That's like saying I can't put my key in the door because someone super glued it, which is a horrible prank to play, but don't do it.
Does that really work?
It's like, oh no, I gave an idea.
Where'd you guys come up with this? What's the field stories?
I mean, I think worst case would be your key when it's stuck in the door.
You can use a chemical to remove it. It's like a glue.
Yeah, like a solvent.
Yeah, you just have to use a solvent.
It'd take a while though.
How about this right here? Would this be a competitive or non-competitive? Competitive. Misspelled competitive, it's all good. This would be non-competitive. Cool. Inhibitors. Yay? That's what I like to hear. And the crowd goes wild.
Can I ask a question?
No questions.
Okay. So how do cofactors exactly work? Is it just they release chemicals that help the enzyme?
They help the enzyme get a specific shape.
Oh, okay.
They help the enzyme achieve its conformation. The last thing I want to get into today is going to be something over allosteric regulation. So let's kind of go there real quick and then we can be done. What allosteric regulation is it can result in either an inhibition or stimulation. Or stimulation. Of an enzyme. Now, this is a little too elaborate to draw, so what you can do is you can kind of just remember that this is in your book. But let me show you what's going on here. Let's say I have an enzyme that is in its active form at this point. It's in its active form because you have these 4 active sites. So these are all the active sites. Now notice what happens. You have this chemical that comes and binds to it. Do you see the chemical right there binding at this point right here?
Yeah.
The reality of it is, and it's not shown, but these guys, these 4 units, are sliding past each other all the time, changing the shape of the active site. So it's active, but it's got some inactivity because it changes shape so quickly. Now notice this guy comes in. You don't see these guys move around anymore, so this must be an activator, basically, that guarantees that you have a stabilized active form. Stabilized here means that you have a guarantee form that is going to work.
So it just locks it in.
It locks it in position. Now let's say that you have the inactive form down here, and here's the reality of it is that most enzymes go between back and forth, like you're seeing with a double arrow here. They go back and forth between active and inactive form, like consistently, like, if you will, watching a tennis ball on a tennis court, back and forth, back and forth. So you might have a chemical called an inhibitor that binds to your enzyme, and notice what happens to your active site now. Completely shut down. This would be a stabilized inactive form.
And they can switch between these two
These two, active versus inactive, switches back and forth all the time until you have either the activator, I should have said activator, not activation, or you have the inhibitor present to stabilize the one form versus the other. Cool. Now when the activator goes away,
it'll keep moving.
it'll go back and forth, and maybe the inhibitor shows up. Now, do you remove the protein? Do you break down the protein in this case? No, the protein's always present. It just sometimes is in the on position, sometimes in the off position, depending on what switches there, basically. Awesome.